Can we start? Catarina. Catarina. Can we start? Can we start? Can we start? So, good morning, everyone. Welcome to JuliaEO, the fourth day dedicated to the ocean and ocean modeling in particular. Thank you very much to Mr. Gelforge for organizing this day. As a logistics note, let's try during the first coffee break to have during lunch, when we go out for lunch, let's go out together and immediately all together to the main lobby where we normally have the coffee break and try to take a group photo there because the weather is not great outside. Because tomorrow some people start leaving. Okay, so let's start the day.
Good morning, everyone. Our today's first speaker is Simon Silvestri. He did his PhD at TU Delft in the Netherlands, where he developed GPU-based tools for direct numerical simulation of high-temperature turbulent flows and studied the influence of different heat transfer mechanisms on the turbulence modulation. He is now a postdoc at MIT, where he is developing a new generation ocean model within the Climate Modeling Alliance project. I welcome Simon Silvestri.
How do I connect this? Black magic, what is this? Okay. Okay. So today I want to talk a bit about the current state and the future development and vision of the ClimOcean package, or as I like to describe it, a Julia framework for building climate models. Now, this package is developed within the Climate Modeling Alliance, or CLIMA project, which, for who doesn't know, is collaboration between MIT and Caltech that has as the objective to develop a Julia native climate model. So in theory, this model is supposed to be able to learn from data, and as such to reduce significantly the uncertainty on future climate projections. And CLIMA is quite a big project, so it's very present in the Julia ecosystem. There are a lot of packages under the CLIMA organization, and here I'm showing just the major ones. So there is our atmosphere and land model, ClimaAtmos and ClimaLand, that depend on the CLIMA core package. That is a library for spectral element discretization on boxes or spheres. And these packages, these components are coupled through the CLIMA coupler to the ocean sea ice components, oceanalics and sea ice, which are the components that we develop at MIT, and now also in Italy and through other collaborations. And so arguably the most successful package of the CLIMA ecosystem is Oceananigans. It is a flexible solver for fluid dynamic problems. So it allows you to build and construct simulations from idealized to realistic of ocean-flavored fluid dynamics. But today I really want to focus on the ClimOcean component and how the scope of this package changed throughout last year. So to remind what ClimOcean is and what the scope of ClimOcean was, this is a slide I presented last year at the last JuliaEO. So ClimOcean was in its infancy then, it was a newborn, and the idea behind ClimOcean was to try to provide a coupled ocean sea ice model to the CLIMA project. So arguably we could have done this within the Oceananigans library, because Oceananigans is very flexible and can do a wide range of simulations, but in itself, in its own right, it's an ocean model. So we could have done the coupling through Oceananigans, but we decided that a new package was the way to go for mainly two reasons. Because first of all, we wanted to keep the scope of the Oceanicans package very broad. We didn't want to bloat it with all the features that are necessary to specifically do simulations of the Earth, which is a very specific type of simulation. And because the CIS package that we started to develop right about the same time was developed in a new package, Clima CIS, that itself depends on Oceanigans. So the coupling couldn't really happen within the Oceanigans package. So we decided that a new package was the way to go, and we decided to call this new package Clima Ocean. And this name Clima Ocean was quite fitting for the package because typically the coupling between a CIS model and an ocean model is very tight in climate models. So typically the ocean and the CIS run on the same grid, and the interface fluxes between the CIS and the ocean are quite simple when it comes to interface fluxes, even if you compare it with what you need to couple the atmosphere with the other components. And for this reason, typically the CIS model is embedded in the source code of many ocean models. For example, MIT GCM has its own CIS package, and NEMO has its own CIS package, but these models are not called ocean CIS models, they're called ocean models. So we thought Clima Ocean is the right name for this new package, because the only scope was to provide an ocean CIS model to the Clima group. And for this scope, the package was supposed to be very, very lightweight, so we just needed a wrapper around an Oceanigans hydrostatic free surface model, which would provide the ocean simulation, a wraparound the Clima CIS model, so a CIS simulation method that will provide the CIS, and a way to interface the two, so a method to compute the fluxes. And these would run on the same grid, and we would have an ocean CIS model to ship to the Clima project. But throughout the year, last year, we also decided that Clima Ocean was the place where we would implement, well, we would pursue another scope that was a little bit different from coupling with Clima, which is to perform a NOMIP simulation. So this is a standardized ocean simulation that is typically done when you build a new ocean and CIS model. And it consists of 6 repeated cycles of 60-year forcing. This forcing specifically comes from an atmosphere that's provided from reanalysis data, which in this case is the Japanese reanalysis data. And what you do is you do these 6 cycles, then you take the last cycle and you compare it with observations or with other models, and you can assess the quality of your results. So to do this type of simulation, we have other requirements than the one that we need just to couple with the Clima model, because now we need an atmosphere. This atmosphere is just data that we need to download. This data is not on the same grid as the grid that we use for the ocean and the CIS, so we need to regrid that data on the grid of the ocean, and we need a method to compute the fluxes between the atmosphere that we have from data and the ocean and the CIS. Now, here we were at a crossroad. So we can achieve this in 2 different ways. So the typical way to perform the simulation is you download the data offline, you regrid it, you prepare it, and you use it to force your simulation. Then you build your simulation in your small package, you produce your results, you publish your paper, and that's it. And you've done your simulation. But when we saw these requirements, we thought that there's an opportunity here to do something a little bit more. Let's say that we want to change the ocean grid, for example. We don't want to have to re-download all the data, regrid it again, and restart the simulation, right? So we want to have flexible methods that allow us to specify an atmosphere, compute the fluxes between the atmospheres and the other components, to change the grid. And if we do that, which is arguably a little bit more work, now we end up with a package that looks a little bit more like a climate model already. It's not necessarily a climate model, because we only have 3 components. We have an ocean, atmosphere, and CIS. So we're missing a land, we're missing biogeochemistry, we're missing atmospheric chemistry, we're missing land ice, glaciers, and so on and so forth. But this structure resembles a little bit what climate models used to be at the beginning, an atmosphere, an ocean, and CIS. So this is where the scope of the package kind of changed. We said, okay, well, we have this requirement. Let's not just provide an ocean CIS model and have a wrapper. Let's expand a bit the scope of the package to be able to have something that looks more like an Earth builder. So the vision behind this package was to provide a framework where you could actually swap components in and out and build different climate simulations, just like Oceanigans is a framework to build ocean simulations. So the idea behind Oceanigans is that you can build idealized or realistic simulations of the ocean, well, the idea for ClimaOcean would be to build idealized or realistic simulation of the climate, swapping in and out different components. And so I really like the quote from Milan about playing atmospheric modeling like it's Lego. And I thought that it was really fitting for the vision of ClimaOcean. And I didn't get the memo that you already changed to climate, but I guess we have aligned objectives now. So the idea is to have really a package that plays climate modeling like it's Lego, so you can swap in and out different components. So the key features that we need to have to achieve this goal is that we need to have swappable components. So these components need to be low complexity, intermediate complexity, full complexity, or whatever you want, prognostic, dynamic, or driven by data. So we need to have flexibility in how we compose our climate model. And most importantly, we want this model to be a home for surface parameterizations. So just like Oceananigans is a little bit of a sandbox for users or ocean modelers to implement, test, and prototype new ocean parameterizations, we want this package to become a little bit of a sandbox for scientists that study the interface between atmosphere and ocean or ocean and other components to be able to implement, test, and prototype different surface parameterizations. And you'll notice that in the title, I have a question mark on the ClimaOcean name. And this is because clearly with this vision, the ClimaOcean name does not really fit the scope of the package. So we are in a quest for changing the name of the package into something more suitable, but we haven't really converged to a nice name, a name that we like. So it's something that we have to do within the next month. So this is kind of a little bit the vision of what we want to achieve. And now the idea is how do we design a framework that allows you to build climate models? So what are climate models? And there are several different types of approaches for climate modeling or approaches to build climate models. And here I'm showing what I think are two different approaches. So on the left, there's the schematic of the EC Earth model. This is a climate model that's developed in Europe. It's a collaboration of a consortium between a lot of different European countries. I think there's Finland, Sweden, Norway, Italy, Germany, Ireland, Portugal, Spain. So it's what we call a little bit a Frankenstein model, because the consortium does not really develop the components, but it takes already developed components from different modeling centers and unifies them in one Earth system model through a flexible coupler can put in communications the different components. So the schematic as you see it is a little bit decentralized. So it's very flexible. You have one coupler that is one component of the climate model. The climate model looks more like a collection of different components, and the coupler adapts to different components and regrids and computes and puts in communication all these different components. And this reflects a little bit the development process of EC Earth that is very decentralized. And this is opposed to a climate model like ICON. So ICON is developed in Germany and is in the Max Planck Institute, and it's more of a centralized structure. So all the components of the ICON model were designed, thought, and developed with the climate model in mind. So the interface is unified. There is a centralized model that governs the computational fluxes and the time stepping of the model. And this, of course, has some advantages, but loses the flexibility that a model like EC Earth has, where you can swap in and out different components. So these two approaches are completely valid, both of them. They reflect a little bit the development process of the climate model and have different advantages and different disadvantages. And of course, if we want to have a framework to couple different components that has a generalized, centralized model that computes the fluxes, we need to take a little bit of both. So that was the idea. We need to have a model that is flexible, but is also centralized in a certain sense. And the nice thing is that this is possible with multiple dispatch from Julia. You can always adapt you can always have a centralized model that adapts to different components through multiple dispatch. So this is kind of a solvable problem. And this is what we want to achieve in terms of interface. So we want to take the already successful recipe from Oceananigans and Speedy Weather of having a generalized model that takes in different parameters or different components, different schemes, different parameterizations, and the model will change depending on what parameters or parameterization you pass to the model. So we want to have an Earth system model, a centralized structure that takes in different components, ocean, atmosphere, and sea ice, and unifies them all in one central structure. And it's very important that we expose the interfaces to the climate model, because the climate model needs to be the one that computes the fluxes and redistributes it through the various components. So this is the vision. This is what we want to achieve, and we haven't achieved it yet because the scope changed quite recently. So this is where we want to go. But given this vision, I want to show you just where we are right now. So what ClimaOcean can do right now. So one of the most important features of a climate model is regridding. So different components can be on different grids. So you want to be able to interface different components through a regridding process. And the idea of this framework is that the couple model will govern this regridding, but the couple model should also possess its own independent grid. So the idea is the couple model takes the information from the components, regrid them on the couple model grid, computes all the fluxes, and distributes them to the various components. In this way, you can keep the flexibility, but also have the centrality of a model that computes its own surface fluxes. And regridding in itself is kind of a trivial idea because it's just a sparse matrix multiplication between different quantities. The problem is that the regridding needs to be conservative. So you want that the integral of a certain quantities on the component grid and on the coupled model grid should be exactly the same. Otherwise, you start leaking energy and mass out of the system, and that's something that you don't want. So the problem here is computing the weights. That's the only problem of regridding. And especially since in ocean modeling, we really use kind of unorthodox grids. So an example of what we use is the grid on the top right. It's called the tripolar grid. That solves the two problems that we have in ocean modeling. So because of the algorithm that we chose, our grids are supposed to be locally orthogonal, unfortunately. We can change this, but we just didn't get to change it. And we have to avoid the singularity at the North Pole, because North Pole is in a place where you have the ocean. So what we do is we take the North Pole and we just stretch it out in two different singularities that are embedded into Canada and Russia. So we still have a singularity problem, but it's hidden in land, so we don't care about it. So this grid is probably the most simple grid that you can have that solves this problem. Otherwise, you have the cube sphere that is also quite complicated because you have all different local orthogonal systems that you have to take care of. So we didn't really develop yet weights computation framework, but at the moment we use XSMF, that it's a wraparound the famous ESMF coupling package. But we're really stoked for using the conservative regridding package that Angela is developing. So as soon as that's ready, we're going to have conservative regridding that is fast and will work perfectly in this framework. So the next thing that a couple model needs to do is to compute exchange fluxes. So at the moment, what we have assumes that a flux of a quantity phi can be expressed as a product of a characteristic velocity scale U star and a characteristic tracer scale phi star. There's not a strict requirement, but it's what we have implemented right now. We really want to expand this framework to make it more flexible and to be able to accept different formulation of surface fluxes. At the moment, we have only two formulations implemented, one very simple fixed coefficient fluxes where phi and phi star and U star depend on coefficients that you pass to the model that can be spatially varying or time varying. And the standard Monod-Nabokov similarity theory that assumes that a quantity is logarithmic as it moves away from the interface. So you get this kind of complicated formulation that has been derived from wall-bounded turbulence theory. So it's not really exact in the framework of interfaces in climate models. So models typically put a correction to this formula that is that psi function over there, which is extremely empirical. Basically, you have campaigns of experimentalists that go out in the ocean and just measure the air, measure the ocean, and invert this formula and take out that psi function. So there's a lot of space for improvement when it comes to surface parameterizations in climate models. And I think that this will be a framework a field in which data-driven parameterization or machine learning would fit actually very well. And this similarity theory formulation ends up producing a set of a couple of nonlinear equations that you need a solver to solve for. And at the moment, we solve for these quantities with a fixed point iteration solver, very simple. We have plans to improve it with something a little bit more advanced, like a multivariate secant method, but not more than that probably. And the important thing is that as part of the nonlinear solve, we include the interface quantities. So that phi I is temperature or salinity or humidity at the actual interface between different components that is computed as a balance of fluxes with the incoming fluxes from one component and the outgoing fluxes from the other component. And these 5 quantities are really properties of the coupled system. They don't live in one component or another, but they belong to the coupled system. And I think they underlie the fact that you really need one overarching coupled system that governs the interfaces. Okay, a framework to handle climate data. So a big space in the source code of CleanMotion is dedicated to handling climate data. And this is because when you start doing realistic climate simulations, well, you need to force your components with prescribed data, or you need to initialize your ocean or your sea ice or your atmosphere. You need to validate the data you produce with climatology. So it's important that you have a way to retrieve and inspect climate data. So we have built this framework that is based on the metadata abstraction, that is just a lazy representation of a certain data set that can live online or can live locally, can live wherever you want. And this metadata will implement methods to download and retrieve the data from wherever it is located, and will interact with Oceananigans field and field time series type to materialize the data on a grid or on a grid in time, so that we can handle directly interpolation in space and time through this framework. At the moment, we can handle only gridded data, because our in-painting methods are very, very primitive, and we only do linear interpolation. So it would be nice to see if we can extend this framework to use, I don't know, maybe satellite data or some more complicated scattered data that we can use to improve the models. And here there are some nice videos of the JuliaEO surface temperature, that is the atmosphere that we use to force the OMEP simulation. The sea ice concentration from the ECHO dataset, ECHO 4, and sea surface salinity from the EN4 reanalysis dataset, all regraded onto Oceananigans fields and field time series. Okay, so I want to give you a little bit of an idea of how this coupled framework works. So for the moment, we try to keep it as simple as possible. So the whole flux computation happens on the coupled model grid. So the coupled model needs to know what state variables to take from the components and where to insert the already updated fluxes. And this is done through the component exchanger type, which needs to be extended for each other component that you insert in the climate model, and will inform the interpolate state and update net fluxes function on how to take the state variables, how to regrid it on the coupled grid, and how to insert the updated fluxes. And of course, the coupled model also needs to know how to time step the component. At the moment, the workflow is that the coupled model time steps all the components, updates the fluxes, and then you time step again. But we're trying to figure out if there's another way to couple the components more tightly. So maybe, for example, if different components use an RK3 substep or multi-stage time steppers, how to couple in between stages and not only at the end of the time step. Okay, so this was a little bit an overview of what we can do now with CleanMotion, and I want to show you now some examples of some simulations that come out of CleanMotion. So this, I think it looks pretty beautiful, but it's a very, very simple simulation to do with CleanMotion. This is the OMEP simulation at 1/6 of a degree. So it's a dynamical ocean coupled to a dynamical sea ice model forced by a prescribed atmosphere. And I like to call this a GCM in 13 lines because it's the parallel to the turbulence in 7 lines example that we have in the README of Oceananigans, which is the simplest possible simulation they can do with Oceananigans. Well, the simplest possible simulation they can do with CleanMotion is an OMEP simulation. And this is a 2-component system because only the ocean and the sea ice are dynamical. The atmosphere is prescribed, so it does not really feel the effect of the fluxes from the ocean and the sea ice. But the structure is similar to an Oceananigans simulation, so we have a centralized model. In this case, this is called Ocean Sea Ice Model, which is a misnomer, so we also have to refactor this to something more like a climate model or system model. And this accepts 3 components, the ocean, the sea ice, and the atmosphere. And the framework for handling data allows you to download and initialize the ocean state and the CI state from echo metadata. We could have chosen other data sets to initialize the data. Now, this simulation is very simple because it's only 2 components. These 2 components are on the same grid, which is the same grid that the coupled model uses. So there's effectively no regridding going on, except for interpolation from the atmosphere. Now, the next logical step from here was to actually add an atmosphere. And the most logical atmosphere to include at the moment was PD weather, because it's very simple to use and to interface with the coupled model. So this is a 3-component system. So it's an atmosphere, a primitive wet model from speedy weather, a hydrostatic free surface model from oceanigans, and a CIS model from ClimaCIs, all coupled together that react one to another. The interfaces are computed with Monod-Nabokov similarity theory. So to be honest, this is not really a 3-component system. This is probably a 4-component system because speedy weather includes its own bucket land model. But since it's not part of ClimaOcean yet, I wouldn't want to consider it as one component. And you can really see how baroclinic eddies that start developing in the atmosphere really exert stress on the sea ice and a momentum in the sea ice and in the ocean. So this example is still a little bit simple because the ocean and the sea ice are again on the same grid, which is the same grid as the coupled model. So I want to show a last example in which this is not the case. And this is trying to include another ocean model. So that is not even written in Julia. So this is coupling speedy weather with the Veros ocean model. That stands for Versatile Ocean Simulation. That's an ocean developed at University of Copenhagen. Is probably one of the most usable ocean models after oceanigans. And it's very easy to interface in this framework because it's written in Julia. And in Julia we have Python call, which is a very easy framework to exchange information between Python and Julia. So actually this was just, this was very easy to do. In a couple of days, we just coupled the Veros ocean model. And I'm actually very satisfied of the result because it demonstrates how flexible the interface can be. So going forward, the idea for this year is that we need to refactor the package. So ClimaOcean doesn't make much sense. Ocean CIS model doesn't make much sense, so we have to refactor the name of the types and of the package. We need conservative and distributed regridding. For that, we'll use conservative regridding.jl, and we have to figure out a strategy for distributing the coupled simulation in on different workers. We need a land model. We cannot just use the speedy weather one. So we want to introduce a more full complexity land model. We can probably start with a simple one so that we start developing the interface between the land and the different components. And we want to run couple simulation to test the difference between a prognostic and a prescribed atmosphere. So I'm looking at this a little bit more from the ocean perspective. So I want to see how the ocean currents change when you put a prescribed atmosphere or when you have an atmosphere that feels the feedback of the ocean. And my dream would be to add support for Fortran models because, like it or not, that's where the development is in the climate modeling space. Most models are written in Fortran. So if we open a door for Fortran models to work in a coupled framework in Julia, that will probably attract many more users to a Julia coupled model. So yeah, that was all I had to say. Thank you.
Thank you. That was a wonderful talk. 2 questions. Have you considered climate Earth instead of climate ocean, since you're probably going to include land also, at least, otherwise it gives the impression that, okay, it just models the oceans. If you want to model the interaction with the atmosphere in Earth, forget it, go somewhere else, which is not good. So the second question was, given the difficulties you mentioned with the surface interaction model, and I know a lot of the error by meaning unknowns in the climate model have been exactly how does Earth interact with oceans and how fast do trees and the ocean life reacts to changes in temperature and changes in acidity, and so basically the reaction mechanism of Earth. So have you considered just doing an integration over all possible parameters and values to try do a little bit of reverse engineering, saying, instead of saying, okay, if you put these values to get this change of temperature, you say, okay, we have this change of temperature, what are the ranges of values that could explain this? And then look into it. Thank you.
So the answer to the first question is that Klima Earth already exists. So it's actually the couple model of the Klima project. So I don't really want to step on the toes. Like we need to separate we need a separation of concerns. So Klima Earth is just the actual Klimatmos, Klimaland, Oceanaligas, and Klima Sea Ice all together. So this is more of a framework where you can really just test new ideas when it comes to different components or different surface parameterizations, or you really want to focus on the sea ice and add a prescribed ocean and prescribed atmosphere on top and see how the sea ice changes. You know, that enables you to interact with different components without necessarily being like one monolithic climate model like Klima Earth is, for example. And for the second question, it's a really good point. The idea, well, what I would like to do is to calibrate the parameters of the surface fluxes to match with data. So do like a, not really hand tuning, but automatic calibration. You can use like methods like ensemble Kalman inversion, and then you really find these parameters that give you the best results in terms of the actual state of the atmosphere and the ocean and the sea ice. So that will be a really good project to do. It's quite difficult because the whole system is very, very heavy. So doing an automatic calibration it's a very hard computational task. But for this reason, at least for our components, we're trying to make them as fast as possible so that we can do this inverse problem.
Hey, thanks for a great talk. Really excited by this. I wanted to, as you know, there's this climate models GL framework that I've created with a lot of the same goals, but I really started from the other end. Right, so I built interfaces to, in fact, Oceananigans and Python models and all of this. I haven't really focused on the coupling part yet, but I think there's going to be an interesting synergy or complementarity between those two things. The interface that I'm sort of putting forward is much more like the old school models, again with the sense that that's a good way to attract people into our business. My question really was something slightly different. Which is, I'm kind of surprised that you decided to do all of the data merging parts inside, like the data dependencies, and because the regrading. I mean, there is an ecosystem of these things in Julia. Mesh arrays, for example, is something I created to do the regrading part. But there is also, so I'm surprised by this. Kind of, how do you guys choose what is kind of internal versus more modular and external is my question.
We depend on mesh arrays because we one of the data sets we have is Echo Darwin. Echo Darwin is on the lat long capped, so we need a way to regrade it, and there is no problem of depending on other packages that would do the regrading for us, for sure. But then we need to expose the data for I mean, it's good to have a way to visualize and to handle the data internally, because you need to validate, you need to force for example, if you have a prescribed component, you need the data that forces that prescribed component, that populates that prescribed component. So you need to have that data in your model. And if you need to have that, well, then you can expand to other data sets, because the idea is to create a framework that allows you to handle the data. So if it works for one data set, it can work for several. That's the idea. And there's no problem depending on other packages. If there's packages that do regrading, I'll take them. There's absolutely no problem with that.
There is something in mesh arrays that you might be interested in, which is recent. I added the NemoGrid support. And the NemoGrid support is this bipolar grid you guys have.
Orca.
Yeah, it's basically the same you have, right? The two poles. So we might be a step closer to being able to support that. But if I can just follow up on my question in reverse, I'm surprised, for example, that seawater polynomials is not an explicit dependency of Oceananigans. To me, that's an obvious sort of thing to have.
It is.
It's explicit.
Yeah.
I found myself kind of having to be using one and using the other.
You need to use it when you want to. So the TOS 10 equation of state is not an explicit dependency. It's not exported by seawater polynomials. Probably we should export it.
Oh, okay.
Yeah,
okay.
it's
So
just specifically a TOS10 equation of state that is not exported by smoother polynomials.
okay. It would make my life easier because I
We-
have
we can export it.
I have an extension to shenanigans
Yeah,
in climate models GL.
yeah, yeah.
And now I need to figure out how do I get the equation of state.
Yeah, using seawater polynomials .TOS10, but we can export it for sure.
Sounds good. Anyway, thanks a lot for the great talk again.
So I don't work on global models, but I do also work on coupled models, and some of them are in different languages as well. So at our institute, we're using the basic modeling interface from the CSDMS, and yeah, it's just for you to know. Like I made the Julia version of this interface now. And I have some code, for instance, as well to, from Julia, run Fortran models like Modflow through the C API. So I'd be happy to chat about that.
That's amazing. Yeah.
I have no idea, like these Fortran models that you're looking at, how feasible it is, for instance, to build them in Binary Builder.
Yeah, I guess you should build a library that exposes like the time step function in Fortran to Julia.
Yeah, exactly.
Yeah, so that's why I want to talk with Gael, that as an expert in MIT GCM, if he has an idea on how to do this.
So this basic modeling interface is of course not designed for Julia, so it's a bit less flexible in a way, and so I think you have more options. But still we can chat if you want. Yeah,
for sure. Thanks.
Thank you for a great talk. So my question is, you're talking about coupling and enforcing. Have you done any thoughts about data assimilation? Would it be possible to assimilate data into some of these models?
Well, a big part of this project is to try to make the model differentiable. So once we will be there, the idea is to calibrate automatically the model, so basically do data assimilation, or in a sense. That requires the model to be fully differentiable. Well, we can do it with other methods, but the idea is to make it differentiable. So there are bits and pieces in place, but the road is still long ahead. But definitely that is the path that we're following, to try to get a differentiable model that can assimilate data or can learn from data, which is basically assimilate data.
Thank you.
Thank you, Simone, for a wonderful talk. Now we have our next speaker, Andre Nogueira Souza. He is a senior HPC engineer and AI scientist at Rescale and a visiting scientist at MIT, working at the intersection of high-performance computing, applied mathematics, and machine learning for engineering and physics applications. His research interests include generative and physics-informed machine learning, stochastic processes, and scalable numerical methods with a particular emphasis on data-driven emulation. I welcome Andre.
All right, let's see if I can get this thing working here. Okay, entire screen. Okay, wonderful. All right, good morning, everyone. So I'll be talking a little bit about how we can begin building models and AI methods that give us insights that we couldn't necessarily have had before. And I'll go in detail about what I mean by this. This is a project that grew out of work that I did at MIT with several collaborators at MIT, including Simone, who just spoke. So just to give a recap of some of the stuff that we've seen in the conference thus far, we've seen satellites, so ways of making observations of our Earth system, usually on the surface or some integrated quantity along the surface to the satellite. We've seen ocean stuff, either by just staring outside or by looking at Simone simulations. And we've seen lots of different kinds of models for representing, physical processes that we care about or mathematical models we care about. And we've seen various ways of combining models with data, and the SciML ecosystem that Chris has is a good example of how we combine these things together. And for this talk, I'm going to discuss yet another way that we can take data and models and do stuff with it. So the way that I'm going to describe in this talk of this combination is predicated on, let's say, a very classic approach coming from any kind of physical theory, where the goal of a physical theory, in my mind, is to make inferences with less data, whether it's to predict what happens in the future with what we can measure now, so that's an inference for the future, something we haven't observed yet, or perhaps we only have partial information of a system. Like for Maxwell's equations, one of the great successes is that you can only measure along a boundary of something and be able to infer what happens within the volume. So it's much less information that you need to actually make a prediction about what's happening. And physical theories let us bridge that gap between what's observed and what we don't observe and make sensible predictions. But for complex systems such as the atmosphere, the ocean, or in general any kind of chaotic systems, the best that we can do is having a numerical model to represent what the system does. And because of computational irreducibility, we can't just represent it as just some simple function of, let's say, an inverse Laplacian or multiplying by some number in order to say, hey, this is how we make an inference. We have to evolve things forward and see what happens. So then we can go to the next step, where with computational models and data-driven approaches, we can kind of expand this theory plus data paradigm that has existed in physics, but use more complex models. And specifically, I'm going to focus on the inferences part for this beginning part of the talk a little bit about a philosophy of what we mean by inference. And then I'll move on to the specific ocean application afterwards. So as scientists or engineers, we often ask some question about information we have and some inference that we want. So here X represents any kind of information that we have. For this talk, it'll be information about the ocean surface, and Y, the information we want, will be the ocean interior, meaning currents in the underneath the ocean, in the interior, the temperature, the salinity profile, density, etc. And then we have some way of making an inference, this function f. And this function f can be an ODE solver that takes some initial conditions and outputs some final condition. It can be Newton's laws of motion. It can be the Navier-Stokes equation, whatever we want. But the goal here, the point is that it's a deterministic case. Like every single time that we plug in a given piece of information, we only get one thing out. That's the definition of a function. More often than not in science, that's actually not what we want. We don't want just some deterministic answer, like we plug in one value, we get exactly another value out. What we really want is more of a probabilistic inference, where here it's very much the same kind of question, where we have some given information that's again represented by X, some information that we want, Y, but the way that the inference works is that we draw from a distribution. So you ask for a given piece of information and you don't know exactly what it is. You get a range of values of what's possible instead. And there is a connection between this functional form and the probabilistic version, in that the probabilistic version is a generalization of the former. So if we had perfect information and it's perfectly predictive, then this probability distribution, here represented by rho, so not a density, a probability density, then this is just a delta function centered on y minus f of x. So the probabilistic formulation generalizes the other one. Again, just drawing a single sample and only getting a single answer at a time, that's a delta function. So this works really well for cases where functional forms between quantities you care about exist. So here I'm looking at the function y equals x squared as an example. You plug in x equals 2, you always get y equals 4. You plug in x equals negative 2, you also get y equals 4, etc. Plus or minus doesn't matter here. Now, when this starts making a difference is when you start wanting to go backwards. So instead of asking, okay, given y, what could have x been? So let's go through a thought process here. If y is 4, there's two values that x could have been. It could have been minus 2 or plus 2. There isn't a functional form that just gets us from that value to 2. It's two possibilities. The probabilistic formulation allows us to get around that by saying, like, okay, maybe I don't know if it's the plus or the minus, but I can say that it's 50% of the time the plus or 50% of the time the minus. So that kind of branch selection process isn't necessary with a probabilistic formulation. You can kind of hedge your bets, say, okay, it's one or the other. Now, why is this important for machine learning? And how does this apply to what I'm going to discuss down the line with the ocean inference? Is that I'd say most problems in science are this kind of ill-posed nature where a given answer isn't actually perfectly informative of what you want to find. And secondly, let's say you train a machine learning model to find the square root, but you have the plus or minus branch. And you do this whole training procedure. And half the time, the neural network sees like, oh, the square root of 4 is 2, and half the time it sees it's minus 2. If you train a neural network on this, it's always going to produce, eventually the minimizer of that is going to be 0. So if you ask a neural network what the square root of 4 is, it's going to tell you 0. The square root of 9, it'll tell you 0, etc. That's what the training procedure would give you. Whereas with, let's say, generative AI methods, it won't do that. It'll produce plus 2 or minus 2 half the time. So that's the benefit of using something like generative AI already, even from this simple example. So the other benefit of using this probabilistic formulation is that you can do uncertainty quantification. You can figure out, is the given amount of information that I've supplied informative enough of what I want to predict? So that's kind of the functional form situation. That's when you have useful information. The information that you provide to model is actually useful for making an inference. But in the case that your information is completely useless, that input does not affect the output at all, then a probabilistic formulation reduces to the marginal density in this case. And we'll see examples of what I mean by this shortly. So no matter what happens, you still get something informative. And as long as the generative model is somewhat constrained by the input that you have, then you've been doing something, let's say, useful on a scientific level. So basically the former problem is a bit ill-posed when it comes to just a scientific question because a functional form just may not exist. Whereas the latter is always well-posed. Even if there isn't an exact relationship, you'll be able to say something. There is a relationship between the two in terms of machine learning, in that if you train a method to try to find just a deterministic function and it's an L2 loss, then the connection is that line on the bottom, that the function that you'll find is actually the expected value of your conditional distribution. So that's the functional form that a neural network would find, let's say if you do L2 training. So the big difference between what we can do now that we couldn't do before, and it's thanks to this revolution in, both compute, algorithms, and let's say just general approaches of practical engineering to make these systems work, is that both the y and the x can be high dimensional. And what I mean by high dimensional is that they can be images. So you can take one image and you can predict another image. And because it can be this high dimensional object, we can ask, well, much more sophisticated kind of scientific questions. And the method that I'm going to use to let's say, characterize this conditional distribution is a score-based diffusion model, but you can use other methods as well, like flow matching is a good example of other methods. But there is a reason why I like score-based diffusion models specifically, and it's that you also get the score function out of it. And I'll end the tutorial in the afternoon. We'll see exactly what that is. But that object helps you compute many other things as well. So you get for free this extra little function that you can play around with and do more things with. The neural network architecture, personally, I don't think matters too much, as long as you include the right kind of inductive bias. And here I'm using a modified UNet to take into account the diffusion process. So to recap, X, information that we want, Y, information, or sorry, X, information that we have, Y, information that we want. In this case, this X will be the ocean surface, because that's essentially what we measure with satellites. And what we'll want to predict is the ocean interior. And the thing that'll bridge the gap between being able to make what we observe with what we don't observe is going to be an ocean model. And this ocean model I will treat as a perfect model in order for making this inference. So I assume that it is the best, most calibrated, most well-designed ocean model, aka Oceananigans. And it'll do the best job that we can to make an inference of the ocean interior. So in pictures, what we have is satellite measurements of the surface. But really what we want is to put measurements inside the ocean and be able to figure out what's going on. There are actual measurements in the interior of the ocean as well, but I'm going to ignore that for now. So specifically for this ocean inference question, I'm going to take a 3D Navier-Stokes equation, and it's going to have this many degrees of freedom. So it's a three-dimensional simulation. And the important part is that it has the representation of the sea surface height, or the free surface height, as I'm calling it here. And that's something that can ostensibly be measured by satellites. And the predicted information, the thing that we have less information on, is going to be the 3D interior ocean state. And this inference will be drawn from the ocean model itself. So the ocean model has an idea of free surface height. It also has an idea of what the 3D ocean interior looks like. And the game that we're going to play is, well, if I know the free surface height, I can predict the interior. So eventually we'd be able to just take a satellite measurement and predict the ocean interior from that. That's the downstream application, but here everything is going to be more idealized. And here I'm showing some images so that I can be very specific about what we're predicting. So the images on the left, the first column, that's a visual representation of the free surface height. And for those in the know, for oceanographers, this is a double gyre simulation, but in a very highly nonlinear regime. So that's the given information, is that image. And what we'd like to do is predict, in this case, the other 4 images, but it's actually 60 other images that's being predicted by the model. These 4 images are at a 400-meter depth of the ocean. If you take a slice, it's predicting the horizontal velocity, so that's the east-west velocity. That's the first image. The second image is the north-south velocity. The third, up-down velocity. And the last one, the temperature field. But you can actually even ignore the physics, because once you go into machine learning land, it's just, given that image, predict the other images. And that's the kind of thing that you can do nowadays that you couldn't do before. Also, just for the oceanographers, there's in this simulation, I have convection in it as well, so it's not exactly a very traditional double gyre simulation. And to make sure that I'm not doing, let's say, cheating in my examples that I'm going to show you, I'm dividing the training data set in a very particular way, where when I start the simulation, I discard the first 100 years of the simulation. I train on the next 200 years, and then all the evaluations that I'm showing you are on the last 50 years of the simulation, which are 50 years in the future from the last training point of the simulation. So I can be guaranteed that the data that I'm going to present the neural network model is completely decorrelated and independent from all the things that it's seen before, 50 years in the future. Yeah, and that's what the blue, red, and orange regimes represent here. So just showing some results now of what happens when you try to do this inference problem. Again, the given piece of information is that image. And the goal, predict the ocean subsurface state at several different depths. And later on, we'll see what happens when we lose information as well on the sea surface height. So because this is 50 years in the future, and I do have an ocean simulation that saw this sea surface height, the ocean simulation itself produced that image that we see there. And I trained a neural network, again, over that 250-year time period. This is 50 years in the future that I'm going to draw this inference from. One sample of the neural network, remember, this is no longer a deterministic function anymore. When I give it a free surface height, it's going to generate many plausible states for the, in this case, the east-west velocity. But this is one of them. And just looking at the two, by eye, they look pretty similar, but there are actual differences, and I'll show that in a second. But if I draw another sample, it looks like this. And if I take the ensemble mean of the 100 samples that I drew, it looks like that image over there under AI mean. So you see that the AI means and AI samples all look very similar to the ocean simulation itself. And so if I take the difference between the ocean simulation and the AI mean, you see that there are actually some small differences, and that's the yellow region on the image where everything's lit up. And physically, this makes sense too. This is where there's the most amount of chaos and eddy variability. So specifically where you have the meander and the double gyre, and where you have convection in the north of the simulation. So it corresponds to the physics that we know. We don't think we can actually pin down the predictions perfectly in those kind of regions. And the model is saying like, well, yeah, the ensemble mean is actually it isn't as close as it could be to the data that we're observing. But again, I have 100 samples that I drew. And I can also look at the standard deviation of those 100 samples. And so the standard deviation of the 100 samples actually looks a lot like the difference between the ensemble mean and the actual ocean simulation. In other words, the machine learning model knows that it's uncertain exactly on the regions that it's different from the ensemble mean. Stated differently, the machine learning method can tell you when you're uncertain about making a prediction. And that's one of the benefits of using a generative method, that you get that kind of a priori error estimate of like, yeah, I don't think you can make a prediction here, at least based off of how things were trained. You can do this for other components too. This is the at the north-south velocity, and it's a very similar story. For convection, also a similar story. Here you see much more unpredictability in the north of the domain. So that's the yellow region at the top of the image. And again, that's just because we're measuring this free surface height, and it's difficult to, with just that piece of information, to decide whether at a very high, or at a 400 meter depth, whether things are going up or down. And the temperature field, which is, very well predicted since it doesn't have much variability. One other thing to notice, especially about the vertical velocity field, so that's the third row, is that the ensemble mean, you'll see just by eye, there seems to be a little bit more white in the top of it. And that's because a lot of the up-down fluctuations are canceling out to give you essentially saying like, okay, I'm predicting 0. This is very much like that square root problem that we saw before with the plus minus square root. You can't decide whether it's going up or down. So on average, it's just going to predict 0 if you take the ensemble mean. Another point that I like to make, that ensemble mean, AI mean column, is what you'd get if you just trained a regular machine learning model to do the prediction. So you get the regular machine learning inference question with a L2 for free when you do the generative version. Okay, so now I'm going to start saying what happens when we lose information about our free surface height and try to make an inference. Let's see, how are we doing on time? Okay, doing well. So previously I showed essentially what was a full resolution image of the model. But now I'm going to start coarse graining the sea surface height from, well, what you see here to this more pixelated version, to more pixelated, to extremely pixelated, and ask the exact same question. How well can I predict the ocean subsurface if this is the information that I'm providing? Intuitively, if you only give 4 values and you're trying to make a prediction at, let's say, 256 squared other values, you may expect to lose some information. And that is indeed the case. Again, I produce 100 samples, and then I average them. And you just see going from the top where things are informative down to the bottom, the image is changing and becoming more washed out. And this is exactly a proxy for just saying that you're having even more samples of AI. You get a wider variety of samples when you lose information. And when you look at the standard deviation of your 100 ensemble members, you see that it increases as you decrease information. So you're becoming more and more certain about what you can, more and more uncertain about what you can predict when you coarse grain more and more the information that you have. This is a good sign. This is a sanity check. We expect when we use less information to be able to predict less. And well, indeed, the machine learning model does give that to you. And if you actually go to the very extreme, where you only provide the sea surface height average, so you only provide one number, you can actually compare that to, well, what happens if I take my data set and I just take the time average of the entire data set? So the image on the left is what happens when I take the data that the neural network was trained on, and I take a time average of all the zonal velocity fields. The AI mean is what I predict when I take my 100 ensemble members and I average them. And I get that. And they look very similar, maybe a little bit wavier for the AI mean. And I think that's just because I only drew 100 ensemble members. If I drew 1,000 or 10,000, I'd bet that it looked way more like that ocean simulation mean. In other words, it's an ensemble versus time average correspondence here. And if you look at the standard deviation from the data versus the AI standard deviation, they also look the same. In other words, this is exactly the case that I described before, where the conditional distribution is reducing to the marginal distribution. The information I'm providing is completely useless. If I take an ensemble mean, essentially this neural network is just reproducing the existing training data set. It's just drawing samples very similar to what it was trained on, without taking into account the free surface height at all. And similarly for the other fields as well. One thing to emphasize here is that even though making this correspondence between time averages and ensemble averages, the future is actually not is in a statistically stationary state. So the correspondence is a little iffy, but visually you see the similarity. But you can look at more than just these point-wise statistics. What generative AI methods are meant to do is capture all higher order statistics of whatever image that you're looking at. It's really supposed to capture this extremely high dimensional quantity. So the other thing that you can do is you can take various higher order statistics, and here I'm looking at a covariance corresponding to meridional heat transport. In other words, the amount of heat that's being transported at a given level of depth. This is a product of the vertical velocity and temperature fields, so you can already see that it's a higher order statistics because it's a product of things as opposed to just looking at the field itself. And then I'm also taking a horizontal average. So it also needs to look at the correlation between all the horizontal points, east-west points in this case. The blue line is what's given by the ocean simulation, and then the red band is the predictions from all the different ensemble members of the neural network. The main thing that you see is that there's a lot of purple, that basically the neural network is able to actually predict the heat flux very well. Except for that bottom right one, where you have more uncertainty as well. And that's also a good piece of information to have. That, okay, like maybe I'm not perfectly predicting the heat flux, but I know that it's within this plausible range. Again, a higher order statistic, so it's impressive that these models can even get things like this right. Because usually when you use generative models, let me just take a step back, you ask for, let's say, an image of a puppy, and it gives you a puppy, and you're like, ah, okay, good, I got a puppy, great. But for science, we want it to be quantitatively correct. It actually has to give us the right number within 10%. Like, I don't know what it means to get like 10% of a puppy right, but I do know what it means to get the heat transport right. And it's a similar thing when you coarse grain. So at the top, this is when you lose information. So starting from the left, you have the most amount of information, and from the right, you have the least. And you see these red bands just expand, meaning that you're becoming more uncertain about what you can predict as you lose information. And again, this is also replicated with the generative AI model. So far, I've only looked at things at a given slice, and you can also look at correlations across the vertical direction as well. So here, I'm showing the ocean simulation correlation with the ocean surface field, and this is just saying, okay, I take my top level field, I look at the Pearson correlation coefficient at every depth below, and I get these numbers for the different fields that I have. So both for the different velocity components, temperature, and, the different velocity components and temperature. I can also do the same thing with AI, where I would look at this correlation between what I infer for the surface and what I infer for the bottom. And you see that the structure is very similar to the original ocean simulation. Now, this is a slightly different thing that I'm measuring here. Here I'm looking at the correlation between the predicted field. So this is a Pearson correlation coefficient at every depth between what the AI model predicts and what the ocean simulation actually produced. So that's the middle one over there. So for the different fields, you see that the correlation coefficient are pretty much close to 1 for the velocity fields. And for the vertical velocity field, it's a little bit less. It's around 0.8. So that's the green line that you see. The last one is a different measure. I'm pretending that one of the ensemble members that I drew is, let's say, my perfect prediction, and I correlate my 99 other predictions from the neural network to that one that I'm holding out. And from there, you see a very similar structure from the ocean simulation. I'm using this as a proxy for the samples drawn from the generative AI model are similar to the actual observations that we would expect as a ground truth. Whenever you start doing probabilistic comparisons to things that you only have one value for, you have to start getting creative about how you actually make that comparison. And this is one way to say, okay, I have a distributional measure, but I'm only making one observation. How do I reconcile the fact that this sample number is actually similar to one of the samples I've seen before? This is one way. And you can also do this when you use way less information. So when you have this extremely coarse-grained sea surface height and you try to make a prediction. And for the sake of time, I also want to say that you can also look at integrated vertical velocity. So this is a quantity that oceanographers care about, especially physical oceanographers. Basically, it tells you what the total heat transport in the ocean is, and just saying, like, yes, you can take into account correlation to vertical, horizontal, and get a reasonable estimate of what the zonally and vertically integrated meridional heat transport is. For our sake, it's just another higher order statistic to calculate. And you can also calculate yet another higher order statistic, such as the overturning circulation. So the main takeaway that I want everyone here to have is that really that all questions in science really should be formulated as probabilistic inference questions, because that is the more natural way to phrase questions. And the other one is that generative AI, although it's been used for image generation in the past, and we haven't, let's say, tried to be too quantitative about what it means for science, I hope to demonstrate that we really can start using it for science as long as we do a good job with the training. And we can ask questions that we really couldn't, well, we could ask them before, but we couldn't really address it. And in this case, it's how much does the ocean sea surface height constrain the ocean interior? For oceanographers, it's been known for a while that it actually provides a strong constraint. But this provides another way, at least in the context of the models that we produce, to see how much it does constrain the ocean interior. And with that, I welcome questions.
Thank you for a great talk. And I only have one question, which is, when you look at your generative AI results and you compare it with the standard approaches that people use in the field, how well do they compare? I mean, and if you have a ground truth, in the case that you actually know the exact value, because you had some probe going there and actually measuring it, how well does it fit the actual data that you get? Thank you.
Yeah, so in order fitting, let's say, observational systems, that would be contingent on how well the model already does. So here, I'm thinking of this almost more like a theory type approach where in the past for oceanography to do the same problem, they'd use something called the, essentially the quasi-geostrophic equations. Surface quasi-geostrophic equations would be the equivalent, where they take the free surface height information, they basically calculate a more sophisticated inverse Laplacian, and they predict what's happening in the ocean interior. And this instead says, okay, we don't need this analytic equation. We have a whole model that includes all the most sophisticated physics that we know. What if we do that same exercise of trying to predict what happens in the interior with that? So the success of this model with actual observations will be completely dependent on how well the ocean model does at making inferences. Now, let's say you use an ocean model that's already been calibrated to match statistics of the Earth system. I don't know. I've never actually tried it, but it would be interesting to try to see how well this does predict the ocean interior. I know that when people have tried the theory-based approaches, they've been very far off and be able to predict especially the vertical velocity, like by an order of magnitude in the ocean. And I'm hoping that something like this would get you, well, not an order of magnitude off, but something much closer than the previous theory approaches. Thank you. Mm-hmm.
Hey, thanks for this great talk, Andre. I have a question about the what's the unit that you use.
Yep.
So if I'm not mistaken, you use 15 vertical levels in your ocean model.
Yes.
And do you implement the depth dimension as additional channels? Or is this a really truly 3D convolution?
In this case, I used a 2D unit. Okay. Yeah. So a 3D unit, I think, would make more sense if I had more vertical levels. But because I only had 15, a 2D unit included as extra channels, I think was perfectly fine. I think it would do better with the 3D unit, though.
Okay, that's interesting because everybody does it like this, even if you have higher resolution. So I'm just wondering if there is a theoretical reason why the vertical dimension might be really different than the horizontal dimension and better handled as channels, or is there some? It's just more convenient. I don't know.
I think it's because usually you have less vertical, like your the number of degrees of freedom you have is way less in the vertical than the horizontal. So in the horizontal there I had 256 squared degrees of freedom, and in the vertical I had 15. So that's a pretty big order of magnitude difference. And also because I have so few vertical levels, the field itself isn't as continuous as one would expect. So that inductive bias that you get of continuity from the 3D unit doesn't quite apply as well. Like the very top surface is discontinuous from the second level, for example.
Yeah, great presentation again. I'm wondering if you have thoughts about the atmosphere side of things. I've seen applications like this a little bit. I've seen some of your presentations before. I'm wondering if the same methods are applicable to the atmosphere. Has it been done? Do you think it's going to be done?
Yeah, so the approach is very general, right? It just says you have some model, you have something that you want to make an inference from. How far can you go? So to me, an interesting question that you can ask about the atmosphere that's essentially exactly the same question is the predictability question. So we have this time scale of about 2 weeks for atmospheric predictability that people have cited over and over again. But with this kind of method, you could be a bit more quantitative about exactly what that 2-week atmospheric predictability window is, given whatever state that you have. Here, it's not the ocean surface predicting ocean interior. It's the previous day's initial condition, and you want to make a prediction of the next day. So those are the two. Given information is what we know today, and the information that we want to predict is information tomorrow or 2 days later, 3 days later, 4 days later, etc. And so that would be one equivalent of the atmospheric case. And I've seen people apply autoregressive generative models, but I haven't seen people try to ask this science question of what is the predictability window of this given model. The exact equivalent atmospheric question would be if you have surface pressure and you want to predict the entire atmospheric state, which is also very interesting too. But I haven't seen anyone do it.
So your setup was a double gyre, right? And
Yes.
I mean, arguably one could say like there's a specific region of interest in the ocean, and so you would say like, cool, for this region in the ocean, I only need surface measurements in order to infer what's happening below. But how much do you think this actually generalizes to different ocean regions, right? Because in double gyre is very much like a wind-driven circulation. There's obviously many other places where you have very different dynamics at play. Could you, really think about, is there, or like even infer, like what has it exactly learned? Can you therefore only, let's say, I don't know, you were to look at I don't know, you didn't, but like, let's say you only like learned the barotropic dynamics. You know, you can always infer this one, but you couldn't infer other dynamics and so on. So you can kind of assess what has it learned, much can it generalize to other regions?
Yeah, that's a great question. And it's something that like oceanographers can kind of done by hand in a way. Like Carl Wunsch is being the best example that I can think of. He has all these regions where he looks at in this region of the ocean, I don't expect stationarity because of all these things happening. So I don't expect the past to be very informative of the future of this particular region. And I'd say the main thing that, like, you would have to train on the different regions of the ocean because there are different dynamics. But it would be interesting on various respects either to say like, okay, these regions are similar enough to where I can use, let's say, the same latent space transformation to go between them, to use a machine learning terminology, or to just train on the entire global ocean and make inferences that way. And I think mentally the thing that I was thinking about for the future was to train on a full-scale ocean model, like the kind of simulations that Simona has shown, with the sea ice, some reanalysis data of the atmosphere, or even like a coupled climate model to try to do the same inference exactly for this reason that of the heterogeneity of the Earth. The different regions are just so different that I'm not sure that we can translate what I've learned here to other regions. It might be the case that in certain places the sea surface side is very informative, other places not, and that would be interesting to see. If there are no more questions, I'm happy to talk later, and I'll see you guys in the afternoon to learn about, well, how to actually do this denoising diffusion stuff.
Thank you, Sir Andre Souza, for insightful session on inferring the ocean subsurface using generative AI. We truly appreciate your valuable contributions. Now we have a coffee break.
And where's the ray tracing? I want to have like little surface, like shadows and so on. I think that let's look. So I was to look on, if you go on Apple Maps, it actually also shows you the stars as random points on the thing. Is it also random? Yeah. Oh, random. Yes, there. We have the but it's so much cooler if you have actually. It's like, oh my god, exactly.
There's two things that are missing for that to actually make sense. One is to actually have which we can do. So I want to make maybe tomorrow I'll try and rotate that through.
Wait, is the Baltic Sea not connected to the ocean? That seems
so then the sky is fixed to the ocean rotates. And then you also have an observable for the sun.
I don't know.
We're not allowed to simulate right now.
We need to have bridges to cross it. There's a clear separation between Denmark and Sweden.
Welcome back. Now we have our next speaker, Sir Gail Forget. He currently works as a researcher at Massachusetts Institute of Technology and PI or co-PI of projects funded by NASA, NOAA, AREA and MIT Portugal program. His research group is focused on ocean sciences and climatology. To this end, he has developed a series of Julia packages such as mesharray.jl, climatemodels.jl, mitgcm.jl, and driftlers.jl, oceanrobots.jl. I welcome Gail Forget, sir.
Great. So let me pause the movie for a second. I'll get back to this. So in this presentation, really, I'm mostly going to set the stage for George, who is going to be doing the presentation of the work that is started. But I wanted to bring up sort of the context and the goals of this project that we got funded together. Oh, I need to play. So the project that I'm talking about has to do with combining model and observations in the sort of ways that we've already talked about in this session and conference. Specifically, we're aiming to look at two regions of the global ocean, the Azores and the tropical Pacific. It's a project with folks that are here, most of them, Adriana, George, and Jao, and then with Jose Silva as well. We are very thankful and grateful for this opportunity that was provided to us by the MIT Portugal organization program that has funded the project 6 months ago. And so this is a 2-year project that we have, and that's going to allow us to really explore some fascinating questions. The summary of the project is here. In essence, we're going to be bringing the models from the MIT side, and by this I mean MIT GCM as well as Oceananigans and other things, and bring them to the applications that are going to be taking place here, and in collaboration with our colleagues in Portugal, focusing on internal waves and their relation to mixing. I'm taking also the opportunity to tell you the little origin story for both this collaboration and kind of why we're all here today. It turned out that in 2022, on this island, we had this so-called symposium and advancing ocean observations. And I got invited to this. You see in the picture here that there's a couple other people you'll recognize, including Katarina and myself in the sort of top right corner. I have put a link to the paper that summarized this workshop. The sort of key point maybe for today is that my idea for this workshop was to bring the so-called digital twin for ocean robots framework that is written in Julia. And based on that, in relation to that, I met with Jao, who's over there. And we sort of cooked up this idea of the JuliaEO workshop that we have had the great chance that the Earth Center has decided to support it year after year after year. And that's how we are able to get engaged with all of you great people. And it's been a very fascinating chain of events for me. And so today when we are looking at Terceira becoming the Julia Island, in a way, it's this whole funny chain of events. The sort of things that I love about my job. It's like, you meet somebody here, and then you start a project there, and then you end up with something different. So anyway. The Digital Twin for Ocean Robots framework, I've already mentioned the name. I will have a presentation later to talk a lot more about the observational side. But essentially, it's the idea of bringing together models and observations in this kind of interactive way with enabling mutual benefits so that the models can learn from the data and we can use the models also to guide the observational program and decide what observations we need. So there is a whole suite of observations that are built in there. One thing that is in the modeling lineup is these very high resolution simulations from MIT GCM. And so this is the movie that you were looking at a second ago, which I'm going to go back and play. I'm playing it for two reasons. One is that it speaks directly to the science that we want to do, right? So here you're looking at a variable, which is the gradient of sea surface height of the free surface of the model, and that is in this very high resolution model that has an external tide forcing, such that it generates global fields of internal tides. And so you see all of those beams that propagate across the Earth. Animating them makes your head kind of spin a little bit. Right? There's a lot going on there. And so the fact is, there is all of this internal wave-rated activity in the ocean that can have a very non-local impact on mixing. So it's a complicated topic to address. It's one where really you need these highly resolved and complex models. Another reason that I'm showing this is to highlight the fact that I would never have been able to do this without Mackie, the movie here specifically. And so this is something that, with a couple of caveats in the way I did it, such as the fact that the star background is fake, right? It's just random. I think there is some amazing opportunities that come to us from getting involved with Julia and with Mackie especially. And so this is my kind of showcase for that. So thanks for the community that is here and the community that's developing Mackie as well. All right. This movie, if you're interested, is available online. The .mov, I think, is available, and they're all listed on my web page, so you can go there and retrieve that. Okay. Just briefly about climate models GL, since we've been a little bit talking about it, it has relation to some of the other topics we've looked at today. So it's meant to provide a uniform interface to a whole host of climate models, or models in general, and one that is slightly different, I guess, than what Simone was talking about. Specifically, it targets maybe less interactive simulations. So the one that I just showed you, right, this ran over tens of thousands of cores for like a month and month. And as much as I like playing with models, I'm not going to keep my laptop looking at, turned on for 6 months. So it's the way we operate these models, typically once they get big enough, regardless of the language, is you dispatch them to a supercomputer or a GPU cluster or something, and you let it run. And then you come back to it. So this framework operates more in that fashion. It takes a model, provides a uniform interface to it that's simple and familiar to a lot of people, and then creates an instance of that, a folder for running the model, generating the output, and so on and so forth. And it includes Git as part of that workflow. So it's meant to be reproducibility enhancing. Here is the lineup that I have for now. and I'm looking forward to adding more. That's a suggestion to you if you're interested in this approach, especially. I think it's a good way to share your model configurations that have been maybe consolidated. I have one of those for Oceanigans, for example, that I'm going to show in a sec. But also, this is very flexible in the way that it integrates across languages and so on and so forth. So one of my goals, for example, is we have MITDCM and Oceanigans, which are both great, similar numerics, different use case where one is better than the other. So for the simulation I just showed, MITDCM is more ready. It's been done, and it's been widely successful with engaging scientists. But in many other cases, I want to use Oceanigans instead, right? Because it's faster, it's more tunable, it's more fun, and it runs on GPUs. So I want kind of a unified interface so that I can swap between one or the other, depending on the use case, essentially. So this is the roots of this climate models GL configuration. A comment on Oceanigans. I'm really looking forward to using it more. I have been sort of waiting for stability a little bit to be increased. And so this brings me to this slide that illustrates a point that I made earlier about the complexity that comes from the way that sometimes model development goes on in Julia, where we don't kind of have a very clear view on what the internal parameters are, which text file is involved and all of this. And so when, in this example, I updated my configuration that I'm trying to curate and provide stably from 1 year ago to today, well, the results changed rather radically, as you see here. And so clearly I overlooked something. Now, very thankfully, this is fixed, because Simone told me what the issue was last night. I rerun it this morning, and we're now good to go. So it's gives me an opportunity to first, thank the community for supporting me in helping me in that way in addressing the things that I overlook. Also, it gives me a chance to highlight that the huge success story that Oceanigans is, and the promising future that it has. I'm convinced of this. But yet, to make the argument that I'm still debating to engage in my more kind of intensive exercises with it, whether I should wait for the version 1.0, or should I get going now? I'm still, this is one of the things that I don't think I'm the only user having that experience. So it's just, I thought it was fitting to discuss this here. With this being said, now I'm going to turn it over to George, to come over, who is going to tell you about the meat of the project and our goals. All right, thank you.
Oh, yeah. Oh,
Excuse me. Sir, yours, where am I? Our next speaker is George McElghace. He graduated in oceanography from the University of Lisbon in 2005 and completed his PhD in internal waves at the University of Porto in 2012. His main research interest includes satellite imagery of processes with sea surface signatures, including internal waves, near-shore phenomena such as rip currents, river plumes, and fronts. Recently, his research has focused on software development for SAR and satellite elementary, numerical ocean modeling, as well as high-resolution models for accurate representations of internal wave dynamics and their interactions with other physical and biochemical processes. I welcome George, sir.
All right, hi everybody. And before all, thank you so much, João, for the opportunity to be here. Thank you so much. So I guess the talk is a bit different in the sense that you guys are showing the state of the art of what you can do with Julia, and I've barely just began using Julia. So I guess the question on my mind was, how can Julia help me to solve the problems I want to solve? And those problems are related essentially to modeling internal solitary waves in the ocean. So a quick thank you to everybody that has, in a way, worked on the material we're about to see and the agencies that funded us. And although Adriana has already talked a little bit about it, I want to show you a little bit more about what an internal solitary wave is. So the family of internal waves is quite big. We will be talking about internal solitary waves. And I guess a picture might help. This picture is not mine, it's adapted. But I guess it shows pretty well what a solitary wave is, so you guys might just think of it as a surface wave flipped upside down and traveling inside the ocean. The scales, however, are pretty different, so the internal solitary waves can be quite big. Especially in amplitude, so the amplitudes can go to the order of 100 meters, and the spatial scales can go to a few kilometers in the width of the soliton and a few hundred kilometers in the along crest length. The thing is that sometimes I get a little bit of trouble.
Nós vimos aqui, mas no online não se vê. Deve estar a fazer má contacto. Tenta lá tirar de novo. Sorry. Foi o que aconteceu contigo. Tenta lá de novo.
E agora pô?
Vamos fazer má contacto. Então vamos mudar por este. Espera aí. Tenta lá com este.
No worries, no worries.
Estás a usar? Consegues?
Man, this is easy to negotiate. No, no, tá bem.
Deixa eu ver. Tá? Não, espera ainda, também não dá para ser. Tá? Se calhar o teu computador. Não é daí, não é daí. É da ligação dele. Se não faz mal, fazemos de outra maneira. Não? Pronto. Então fazemos de outra maneira. Fazes o filme. Ok, continua para eles. Já tens de outra maneira.
Ok. All right. So sometimes I get in trouble because I will be showing you satellite pictures of internal waves, and for some reason somehow people don't believe that you can see something underwater from space. So I just want to show you a movie that actually what we're seeing is the signatures of the waves. So I guess I hope you guys saw it. And trying to come a bit closer to the audience, because I know there's climate people here and so on, and ocean people, and try to make the case that they are interesting. Adriana has already showed that the algorithm that they have now to detect internal solitary waves is showing, and that was kind of known, that they are quite frequent in the ocean and they are in a lot of places. And by the way, we're going to have a meeting coming up this April about internal waves in Lisbon. Just in case any of you is interested, you can just talk to us. Where, by the way, there are a lot of internal solitary waves. And another thing I wanted to show you is that we've recently found that along the Pacific cold tongue, so I guess you guys have heard of El Niño, so this is kind of the opposite, it's La Niña. During La Niña you have this cold tongue spreading across the Pacific. And right at where the thermal gradients are stronger, you have direct generation of these waves. So they're not tidally generated as usual. They are generated by these currents and across these temperature gradients, which I guess represents almost a direct passage between very big scales and then through intermediate scales, which I guess is the internal solitary waves, and straight to turbulence. Because in fact, and this is just a zoom, so the island is right here. So it's that yellow thing, oh, it's here. So that's the island we're on. So the scales, as you can see, they're pretty big. This is Terceira. Because what internal solitary waves what they really like to do is to mix. Eventually, at some point, they're pretty good at advecting energy, transporting from somewhere to somewhere else, but along the way, and eventually, what they really do is they like to mix the water column. This is pretty well known. This is not ours. It's from Sam Havens, from the Newcastle University. But what we recently found out that kind of complements this is that internal solitary waves, they also fabricate, in a way, their own surface wave breaking. So although they're traveling underneath, on the surface, they increase the amount of surface wave breaking. So that means some kind of contribution, I guess, to this exchange between the ocean and the atmosphere. So to try to put that in perspective, the traditional view, when you put internal solitary waves alongside other ocean phenomena in this time space plots, I guess what this shows is that perhaps their area of influence is bigger than previously thought, in the sense that they extract energy from the larger scales and they tend to deposit that in the smaller scales. And me and Jose, we always come back to this analogy of Robin Hood, in the sense that they facilitate this energy transfer from the larger scales to the smaller scales. So that's kind of where we are or were. And again, satellite is really nice. You even get sometimes you even get a sense of motion if you use geostationary satellites. But the point is that we need more tools if we want to learn more. And a few years ago, we turned to modeling, and we turned to Martin Bausman, to whom we are very thankful. And he modeled, using MIT GCM, these waves in the Mascarene Ridge, which is in the middle of the Indian Ocean. There are some pretty powerful waves there, almost 200 meters in amplitude. And that clearly showed us that modeling was definitely the way to go. So we continued to pursue that. And we did a couple more works with MIT GCM, including off the west coast of Portugal, where we found out that actually internal solitary waves, they can play teamwork with wind. So if wind is blowing on the top of an internal solitary wave, what it will do is it will mix the water column much more effectively. And we modeled that with MIT GCM. The modeling results look ugly, but they're intentionally like that just to highlight the instabilities in the case that when comparing wind and no wind background stratifications. But unfortunately, about a couple of years ago, a year, 2 years ago, we lost basically the computer broke where we were running these simulations with Martin. So we were left without this precious tool that we were just beginning to understand and explore. Fortunately, however, João and the Air Center and Adriana, they facilitated the opportunity to install the model here in Açores and run it, and that's exactly what we are. So that's the point where we are right now. And with the goal in mind to go back to these waves in the Pacific and understand a little bit more about their energetics. Because I think it's very interesting if you have a direct passage from a very big scale to to turbulence even. And we want to learn more about that, and that's part of a project we have with Gail. Gail already showed that, I'm showing it again. So that's ongoing. And going back to, I guess, the topic of the workshop, which is Julia. So I was completely new to Julia about until 2 weeks ago. And Gail kind of challenged me to do a couple of notebooks. And what the most logical thing to do was, of course, with remote sensing, which is my background and in a sense what I still do, and with SWOT. So these 2 notebooks, I will upload them to GitHub, and I kind of logged my thoughts and, you know, how I felt the code was, how the code was feeling to me. And thank you very much to the guys that developed all these packages for NC datasets and MIT GCM and Cairo and Maki. But I think the point is, it went reasonably well, and of course, like any coding language, you need time, right? So time will make it easier. So that's the one for satellite. This is the one to immediately take the binary data that comes out of the model and just have some diagnostic plots. That probably this is the one I'll be using the most. And of course, hearing about shenanigans and seeing all the wonderful things it can do, and talking to you people, I guess, although the answer right now is no, maybe not use it right now. In the future, I'm pretty sure it's probably the only way to go. It's to use shenanigans. But I'll be happy to talk to you guys over the breaks a little bit more about it. So thank you. That's it. Thank you.
Thanks for this great talk, and I'm happy that you use also NC datasets. And you mentioned that you mentioned on the slide you couldn't download data directly from the internet. So I guess what you mean that you cannot use directly an URL inside NC datasets. That's what you wanted to do, and
I think I also realized they have an opened up. Maybe that's the way to go, I guess.
Yeah, exactly. Yeah. So if you have opened up, then it's the way to go exactly, because NC datasets directly integrates with opened up, and actually it's implemented in NetCDF itself. It's not, and so you download exactly only the subset of the data that you need. Right. If you would just, you can also in Julia you can download a dataset just with the download command, but typically, this downloads everything, and it downloads everything every time you run the notebook. So typically, you would download it once and cache it. Right. But if you have opened up, that's definitely the way to go. Yeah.
Thanks.
So I wanted to follow up on that. Just a brief question. So I'm finding myself doing exactly that, to download as we speak, or I should say my postdoc is processing it all, the entire glorious quarter of a degree set of 3D fields. So we ended up writing, loops and bringing things by like month, and so some overhead essentially to using. I'm wondering, my question is there like a standard recipe to such a use case where you say, okay, this is a thread server in this case, open that, just get me the whole data collection and chunk it, put it to disk. The reason I'm doing that, of course, is because I want to then do computations on it, right? Is there like a recipe or an interest in kind of getting to that level of automation? Distributed
where you can write anything, any data set locally, but it does not do it quite intelligently with chunk. But since it's a PR of you implement it with this array, that should be quite interesting.
I think the SafeCube data function in Açores would be able to do this. I mean, if it takes very long, we don't have basically checking yet, so we don't have breakpoints yet. But basically, SafeCube takes the chunking into account, and basically you can load, and then you can. There's also ways to basically make multiple netcdf files into one disk array that it looks like one disk array, and then you can save it, and then you can set the chunking, and then you can, and then this will try. That's long. Yeah, I mean, it's. Yeah, we don't have checkpoints yet, so if it fails in the middle, that would be bad, I think.
Yeah, that's what I mean. But thank you.
Yeah.
So I guess I'm taking over the question session, but to you, George, first. I suppose you came from MATLAB in terms of your data analysis pipelines. How do you feel about Julia as a kind of a newcomer? I think it's a...
Well, after seeing all the talks you guys have shown and all these libraries and I think I have to do it, right? I mean, it's the future. I don't have a choice now.
Yeah.
Yeah, you guys had me at hello. Yeah.
We're sorry.
No, it's fine.
No, but it's awesome to hear.
I
right?
took the red pill or whatever,
because
the blue pill.
bringing in people like yourself, I think is one of the things that I'm trying to do, and so I'm delighted to hear that.
Thank you, and yeah.
Maybe I can ask a quick question to Simone, or to, I guess, the Oceanigans community, in terms of, for this sort of configuration we're looking at to do internal waves, what's the readiness level of, or do you have examples already, or something like this?
I think with respect to simulation,
Who wants to? Huh? Ah, sorry.
So I saw the simulations that you were doing were non-hydrostatic with a fully nonlinear free surface, right? So what we have right now is we have a non-hydrostatic model that works very, very well in boxes domain. In more complicated domains is a little bit slower because the speed of Oceanigans in non-hydrostatic framework is because of the pressure solver that is done in a very quick way. That is what is heavy in MIT GCM when it comes to non-hydrostatic modeling. We have a free surface in the non-hydrostatic model, but it's only linear. So I don't know how much the nonlinear part of the free surface matters in an internal gravity wave simulation, but that's something that we don't have at the moment. And when it comes to switching to Oceanigans, if you want, we are talking about releasing a version 1.0. So after that, the API should be stable.
Hi. So this is a slightly different question. You showed the visualization, the example of the internal waves in the geostationary satellite images. Is that something you have been working more with, or that you have some projects ongoing with, or was it an example from some other article?
Internal waves in satellite images.
Yeah, in the geostationary satellite images.
In geostationary, we used it, for instance, to take out phase velocities, which is a very important parameter. Not very often, but when there's nothing else, we look in geostationary satellites. And they're not always very visible on them. You need the good sun glint conditions and so on. actually that particular region of the ocean, off the Amazon shelf. That's, to my knowledge, that's actually the only place where geostationary satellites can see them well enough. Yeah. So, thank you.
Thank you, sir. Now we have our next speaker as Alexander Barth. He is Associate Professor at the Geohydrodynamics and Environment Research Group at the University of Liege. He obtained his PhD in 2004 at the University of Liege on data assimilation in nested ocean models. After his postdoc at the College of Marine Science of University of South Florida, he worked on variational interpolation with DEVA and DEVA-END, and he is principal investigator of several European projects aiming to apply and improve these tools for generating climatologies based on in-situ observations. Recently, he also investigated the use of machine learning techniques with ocean remote sensing data. I welcome Alexander Barth.
Okay, great. So thank you so much for having me here. I guess I will slide ahead. So thank you so much for having me here. I will speak today about generative deep learning for inverse problems in the ocean. And in the second part of my talk, I will also speak over more infrastructure packages to handling dates. So I'm really happy to come just after Andre, or not directly after Andre, but he set the stage really well for the question about inverse problems in the ocean, and particularly with generative AI methods. And so generally, like him, we are describing the state of a system with a large dimensional vector, x. So x can be, for example, the temperature, velocity of the ocean defined over a certain grid, but it can be quite generally also maybe just an image where you have a matrix of red, green, blue values. And for a geophysical problem, our state is often not completely known. Okay, so we have to live with this kind of uncertainty. And our knowledge and lack of knowledge is fully described by underlying PDF, probability distribution functions. Okay, but this PDF we don't have directly access to, and so the idea in many of these generative AI tasks is, can we learn this probability distribution function based on data? Okay, and this is, in a nutshell, the basic approach of the basic idea of several generative AI methods, like generative adversarial networks, diffusion model, or flow matching models. Okay, and specifically, flow matching is learns a mapping between a complex data distribution and a simple distribution, which is often a Gaussian. And it's actually quite similar to diffusion models, but it's unlike diffusion model, which using the diffusion process. The flow matching uses the advection process. And as an oceanographer, and I find it quite interesting that these two state-of-the-art techniques for generative AI use actually processes from fluid dynamics to learn really complex data distributions. Okay. So generally, the function is nonlinear because we are mapping from a really complex distribution to a Gaussian distribution. And this mapping function is also called flow, and it must be invertible. So you have to go from a data distribution to the simple distribution and backwards. Okay. And we don't do it in one step, but we're doing it iteratively multiple steps. So that's also similar to diffusion models. You have a complex problem going from these two data distributions that you break down in a lot of simpler problems by doing via intermediate steps. And this mapping function is implemented by neural networks, but as we know, in general, neural networks are not invertible. You cannot compute the inverse of a neural network. And so the idea is that you use the advection process. So the neural network provides the velocity in which you would need to move in this high-dimensional state space. So X is a state space, typically high-dimensional, and you're moving in this space by a velocity which is prescribed by a neural network. And as oceanographer, this is very obvious. If you know where some object in the ocean goes forward in time, you can, by flipping the sign of the velocity, also go backwards in time. Okay, so the inverse comes really kind of for free by just flipping the sign of the velocity. And yeah, so that's the essential idea, how we can create an invertible function based on the neural network. And so the conditional normalizing flow was introduced by Lippmann in 2023, and they provide a tractable way to learn this kind of model, to train this kind of models, and just have a look at this picture to explain how it works. So you have your complex data distribution on the left and your simple normal distribution on the right, and you want to create a mapping between complex and simple. Okay. And you start with one sample of your data distribution, really chosen at random. And then you pair it with a sample of your normal distribution, equally chosen at random. Okay? And then you're simply saying, okay, my flow should be more or less a straight line. You pick a random point at this straight line, because we have to know also the flow at intermediate step. And you're saying that if I would be at the position x prime, my velocity should be pointing towards x0. Okay? So, and this is essentially the training objective of a conditional normalizing flow model. And when I first learned about this technique, I found it really surprising that it actually worked, because how do you know that x0 is the right pair that you should attribute to x1? Okay? How do you know that x1 should go to x0? And in fact, you don't know it. You don't know it. But you pick the point at random, and in the end, high probability regions from your data distribution will converge to high probability distribution, high probability region in your normal distribution, in your simple distribution. Okay, so the training objective, you will never run the cost function of your training loss to 0, but the optimal state of the flow will give you the optimal mapping between the data distribution and the normal distribution. Okay. And you can really learn arbitrary PDFs. So here just you start with a random distribution of points, and then you have your flow on the right-hand side, which moves this point around, and you can really learn a mapping between any kind of functions and any Gaussian distribution. And it's inverse by just flipping the sign. Okay. So this allows us to create now samples which are coherent with our underlying training data. Okay. But now the next thing is that what we want to do, we want to create some samples for which we have some a priori information. So think of if you have a generative model that creates images, if you want to have images of a dog, and then it will just create images. You want to steer the creation of images by a given prompt, for example. Okay, but in oceanography we don't have prompts. We just have saying, okay, I want to create an image based on some observation that I had at discrete locations. So the observation that we have are kind of the equivalent of the prompts in image generation. And actually, this is a solved problem, I would say, from the mathematical point of view, because we have the bias formula. Okay, the bias formula gives us exactly what the posterior PDF should be, given an uncertain state and potentially some uncertain observations. How do I combine a state with observations? This is actually exactly solved by the bias formula. And so we checked with a 0D case that indeed the flow matching models, when it is conditioned by an observations, potentially with noise, it gives us the right posterior PDF that what you would expect by the bias theory. Okay, and then we tried to we applied the neural network also to some data from CMEMS. So that's a subset of the miniaturancy model here. That's the resiliency. So we trained on 34 years of data. We used 1 year for validation, where we tuned the configuration of the unit, the number of layers, the number of channels, and so on. And the last year is for testing, and all I show here is the results for testing. Oops. So you have some temperature and salinity. That's the data that extract. You have some observation at a discrete location. And then we are running the flow matching models, and what you see here in the iteration is the advection time within the flow matching model, and which takes into account the observation to create a field which is coherent with the observations. And also, we are not only reconstructing the variable which is observed, temperature, but also salinity. And we don't have any observational salinity, so it needs to learn cross-variable correlation, as you have also seen this morning with Angra. Okay. And similar to a diffusion model, you get not a single estimate, but various estimate for the same observations. Okay. And then when you have a statistics, you can use also compute the mean, and 100 ensemble members seems to be a good choice, which I will use also here. And of course, the mean is much smoother than every single estimate, and that's really by design, because you don't have information at every single filament, at every small scales, if you have only a sparse observational network. And just as if you would learn a classical neural network in a supervised way, sparse observation, full field from a model, you would only have access to some kind of this smooth representation. But with generative method, you can also actually give a realistic estimation of small scales. So one of the techniques which is quite often used in this context is called the ensemble transform Kalman filter. And we're just using the update step of this ensemble transform Kalman filter, which is often called also ensemble OI. And that's our baseline with which we compared our technique. So, and we have seen that for the validation test data set, we are providing better results than this ensemble OI methods when it's set up in a similar way. So the ensemble OI has also access to the training data set, and it's actually used to represent its underlying error covariance matrix. But one crucial aspect of most Kalman filter-based techniques, or indeed almost all used in operationally, is that they're using the assumption that the data set is Gaussian distributed. Okay, so that when updating the information, you can use linear relationships, and this is something that this is a quite strong assumption that we can get away with by using neural networks. And now we get an ensemble. Is this ensemble any good? And we can, in the context of probabilistic weather forecasting, there are several scores that have been introduced. One is the continuous rank probability score that can also help you to assess whether your ensemble is actually statistically reliable. And so that's the reliability column. Small values are good for reliability, and we've seen that indeed we had a lot of improvement relative to the ensemble Y technique. And another way is looking at talagram diagrams, where the talagram diagram should be flat, and indeed the continuous flow matching also improved relative to optimal interpolation. Okay. I will now switch to another part of my talk, which is more about an infrastructure package. If you have any burning question about flow matching, I can take it now. Yeah?
Just the relation between the velocity and phi, v and phi. I didn't understand the step.
Phi.
Yeah.
So
I think
phi,
you heard me, right? The
phi,
relation between v and phi.
Yeah. So phi is the function that maps between the simple distribution to the data distribution, yeah, and v is how you should move it at every time step. So the relationship mathematically is this. Is this advection equation? Okay. So it's more easily to understood as every sample that you're just moving it. Okay. And phi tells you how to transform the. So phi is kind of the integrated velocity. Okay.
Yeah, I was wondering if you saw any of the work that we did on the hard constraints flow matching methods, and whether you looked into these at all for this kind of application, because it seems like you might have some hard constraints in this kind of problem that you might want to be imposing in this case. I don't know if you'd have like a non-compressibility or something in your fluids, but I'd be curious to see whether there's an application there for that.
I have to say I'm not aware about this work, but I will be glad to learn about it. But the way that we implemented the observations, it's actually what we call a weak constraint, in the sense that observations themselves also have errors. But at a larger scale, in the larger picture, of course, there are hard constraints in the ocean, like you want to still conserve mass, or you want to conserve change in mass only within certain bounds. Yeah, that's certainly useful to apply when you go now to a full ocean model and to try to restart it, which is something that we want to do, definitely. Yeah.
Yes, I'm just here like wondering what could be like some physical interpretation of the probabilities, because when you measure, obviously you're going to be capturing the oscillation effect, but then when you go to the probabilities, what's actually going on? Because one way you can have, let's say, the mean flow, or perhaps you could have the flow which is undisturbed by the perturbation, so which are not exactly the same, even though they can be quite similar, but strictly speaking, they are not the same. So I'm just wondering what could be this probability. And I think you mentioned that the Gaussian distribution is one way to do it, but then you mentioned also there are other ways to do. So also how this interpretation could change upon the probability that you use.
So the physical interpretation is as, for example, the Gulf Stream. Yeah, you have the Gulf Stream flowing one kind of path most of the time, and sometimes the path is shifted. Yeah? So you have the Gulf Stream, which has two different states going from one to another. And the probability function will tell you what is the probability to be in one or the other state. And if you're using a traditional method which only looks at the Gaussian distribution, they will give you a mean path. Yeah? And the mean path is maybe something which is quite unrealistic physically. Okay? Because there's either one or the other state, but the mean is actually might have a lower probability. So think of it if you have a distribution with multiple peaks, multiple modes.
Okay, that makes more sense because yes, if you have like one direction and the other one, and if you think about the very simple state, it could be like 0.
Yeah, exactly.
The mean.
Yeah,
so
yeah.
Very interesting. Thank you.
Yeah, thanks again for once again a great talk. I'm wondering about kind of high-dimensional application. So let's say that I have a kind of observing system that gives me 1,000 variables that are going to be collocated in space and in time, and I have collections of those. So I don't see why this would not be applicable to this. I'm wondering if there is anything that would get in the way to making advection like this 1,000-dimensional thing. And then the corollary would be, how do you handle the correlation and the cross, the probability being graded between variables, dimensions?
So yeah, exactly. So the flow matching technique, like also diffusion, they are really made for large, high-dimensional system. So that's really nice, and that's a property that we have also with a lot of ocean variables. So they don't. So they should also work with high-dimensional state vectors. And how now the relationship between different variables come from, and this comes actually from the flow. So the velocity that it's in this high-dimensional space, that's learned by the neural network. So it's kind of, if I go back to this image, it kind of knows that some variables, it kind of learns that some variables are not really independent, but they are related in pushing the state towards this region, which are known from the training data set. Okay, I propose that I switch now to the more infrastructure work about the handling times. So there is this climate and forecast convention about metadata for Earth data. And one aspect that I interact quite often with is how time instances are encoded. And if you work with netcdf data or also with SAR data, you always have seen that time are actually represented at seconds since the starting date, for example. Okay? And the CF convention defines this kind of format and also several calendars. And before, in Julia, so in Julia we have already quite nice packages for handling times, and they use internally a 64-bit integer counting milliseconds since the starting time. That's for daytime. Okay, and when I first was exposed to Julia, I thought this is actually a great compromise. So 64-bit integer with millisecond accuracy, it's actually quite useful. That is a good compromise, an excellent compromise between resolution and dates that you can represent. And in CF time, I initially use the same approach, but some users actually use much finer resolution. For example, nanoseconds. So I had one user asking for, well, actually several users, two users asked for times resolution within nanoseconds. Okay, and not only the data was then at the resolution of nanosecond, but also the time origin. Okay, and for me as a physical oceanographer, I was asking, does it really make sense for oceanography or climate science to have the resolution at the nano precision levels? So if you are in a boat, when you deploy an instrument, the instrument often does not have any time information. So you're standing with your watch and taking note of the time, and does it really make sense to have something at the nano precision level, nanosecond precision level? But in fact, it is allowed by the Climate Forecast Convention, and it's also possible within NumPy. Okay, and a lot of users use Python. So if NumPy allows for nanoseconds and even down to attoseconds, there will be a lot of pressure to also to allow to read this data with the same without any rounding. And also there's a Python CF time packages which allows up to microsecond precision, so even also higher than our milliseconds. And also X-Array and Pandas default to nanoseconds. Yeah, and so essentially this was, there were some good reasons also to support nanoseconds for the CF time packages. But one of the problems in NumPy, you have even attoseconds precision, but only with a fixed time origin, which is the 1st January 97. Okay, so if you're going down to attoseconds, you can only representing plus or minus 9 seconds around this time origin without overflowing the 64-bit integer. So it doesn't really make sense to allow this high time resolution without also allowing a flexible time origin, in my opinion. So that was actually the approach that we use in CF time, in the new version of CF time. And in fact, internally, we first define a duration, a time period. The duration itself is just a number, but all of this information that we need to interpret this number are type parameters. So in these type parameters, you see a factor and an exponent. So a little bit like floating point numbers, the duration still need to be multiplied by a certain factor and certain exponent in order to compute the actual duration in seconds. Okay. And with this, you can use as a resolution day, for example, and using then the number of seconds within a day within a factor, or you can also by having higher exponent higher than 0 to have smaller divisions, and you can go down to attoseconds if you like. And also the time itself, the duration itself, is also parametric, and it can be an integer 64 or a higher precision integer if you want. And for the duration, similarly, the duration is now also uses the origin as a parametric type. So if you have a large array where every element would have the same time origin, the same time resolution, then this information would only be stored in the type, and it's really very space efficient as well. And the compiler, if you're comparing two different time instances, which most of the time will have the same time resolution and time origin, the compiler sees exactly and can just make a subtraction between two numbers without making any conversion. So I think this type specialization of Julia played out quite nicely in this case. And then we can convert dates, times expressed in Julia with date or date time without any loss of precision. Also, we're handling all the cases that can be represented by NumPy's datetime 64 object, and also Python CF time, where the precision is down to microseconds. And also R, which is quite interesting. It uses actually a double precision floating point number to express the duration. Since a given timestamp, this can also be expressed in our case without loss of precision. And we did some benchmarked, and it's we will see that we were 100 times faster than the Python CF time, but that's because the Python CF time package only implements an object for the scalar datetime, but does not implement a type for an array. So that's That's the main reason why we are so much faster than Python. And you can also experimentally, so there's also experimental support for GPUs. It works on AMD GPU, unfortunately not for CUDA right now, where you can run this code as well. So all of this annotation, type annotation, the compiler is quite capable of abstracting them away. Okay, so in conclusion, I talked in the first part of my talk about the flow matching model that generated some where you can generate some states guided by noise observations, and it's coherent with the Bayes theorem for a simple case that I tested. And we are showing quite competitive RMS errors and CRPS, continuous rank probability score metrics, when comparing to a update scheme from the ensemble transform Kalman filter. So it's essentially an ensemble Y. And for the CF time, I used some, I made some improvement that it makes it much more flexible and to handle different time instances. And just for fun, so last year I presented to you how to compile Julia to WebAssembly to run some ocean models, some really simple ocean models, 2D, 1D ocean models in your web browser by using WebAssembly and the Julia source code. And quite interestingly, so we use GPU compiler for this. You can also run Julia on these really small devices, which are called ESP32. These are really widespread devices that you most quite likely have at home in some smart appliances. And interestingly, they're using the RISC-V instruction set, which is an open instruction set. And LLVM has a quite mature backend for RISC-V, unfortunately not enabled, so you have to enable it yourself. And then you can start to cross-compile Julia code to run on these small devices. Obviously, this you have only 4 megabytes of flash. You don't have space for the whole Julia runtime. And so you have to be, things like allocations, things like this are a bit complicated, but you can cross-compile Julia code to these tiny devices. And here, if you are interested, here's this link, how you can, for example, run this LED strip on an ESP device. Thank you.
Yeah, just on this point. So one of the things that I'm involved with is folks that are deploying Argo floats, and some of them now have a kind of a Linux core on them. But this seems to me that this will enable putting Julia applications on much kind of low power,
yes,
low memory, like very tiny ocean observation device, right?
Yeah, exactly. So that's so if it's a Linux computer, it's more similar to a Raspberry Pi, which is in fact a full computer, and you can run the complete Julia binary on a Raspberry Pi. That's relatively easy to do, or relatively straightforward. But these devices are much smaller, and actually they don't have Linux. They have a kind of that's FreeRTOS, which is running here. That's a real-time operating system, so a really specialized operating system for this case. So it's a really extremely constrained device, and you see it has only 4 megabytes of storage, and you have to also include the OS within this 4 megabytes. So it's really constrained environment. But typically, these are programmed in C or nowadays also in Rust. But maybe if this takes off, we can also use some nicer language like Julia to run on it.
Thank you. During the part on the CF time, you also mentioned the satellite and the satellite orbiting at 10 meters per second. Often I encounter data that's stored as seconds and some timestamp, but not due to seconds, actually actual seconds. Is there also a way to account for leap seconds in this, or is it still something I would have to do manually on the side?
That's a great question. That's a great question. So yeah, I have been in talk with some people from CF convention to better understand how the leap second is handled, because in the latest version of the standard there are actually 2 new calendars that have been introduced. One to precisely taking this problem into account, the leap second issue. But unfortunately, they are not yet supported by CF time. But it's certainly something that's in scope and that I would like to do. But but unfortunately, right now it's not supported. And also, it's not that clear to me how to convert. So in CF time or in NetCDF, I like to convert directly to the Julia datetime, which most people are aware, which most people like to use. And this time object is not actually leap time aware, leap time seconds aware. So I don't know if this conversion can be made. If I have some data set which tells you, now I use leap times, or no, I don't use leap times, can I convert them as they are now to the Julia daytime, which is leap seconds unaware? So it's not clear what should be the default behavior there for me.
Yeah, it's just maybe a slightly related question. Is there a CF convention checker in Julia? Do we have if I give you a NetCDF file, can you check that it respects the CF convention in general?
Not in Julia. I'm not aware that there's a convention checker in Julia. There are some in Python, and there are also some online services. But I'm not aware that we have a CF convention checker in Julia.
Okay, maybe something to think about.
Thank you, Sir Bhatt, for sharing your knowledge on ocean modeling and data assimilation. Now it's the time for lunch, so you are welcome.
Let's go to the main lobby, the bar behind the lobby, normally where we have the coffee breaks, to try to have a good coffee.